This video takes a look at conservation of momentum in a very special case where energy is conserved. It's a really important concept that energy in collisions is only conserved sometimes, but momentum is always conserved. And why is that? It's a really important result of Newton's third law. As we do more and more with mechanics, we recognize that Newton's third law seems pretty straightforward, this action reaction, but as we study more about it, actually it's very profound. It's actually the underpinnings of relativity. Sometimes folks will refer to action reaction pairs, but the forces don't come in pairs. It's actually just one force, and it depends on your point of view. That's why the direction of the force is relative to your point of view. And that's where the minus sign comes from. Then if we consider that forces cause impulses, so impulses are going to be equal and opposite, then that means since impulse causes a change in momentum, the changes in momentum are going to be equal and opposite. And that's conservation, because one's gain is the other's loss. So the total change in momentum is zero. Or we could expand it out and put the momentum terms before, the total momentum before, and equate that to the total momentum after. So all three of these are different ways of expressing conservation of momentum, which again is always true because of Newton's third law. But energy is not conserved, and we have a numerical scale of actually measuring the degree to which energy is conserved. On a scale of 0 to 1, where 1 is perfectly elastic and 0 is perfectly inelastic. And this is called the coefficient of restitution, which is the difference in the velocities after divided by the difference between the velocities before. So it's easy to see why this is 0 if they're inelastic, because then the velocities after are the same number when they stick together. So that's why that's 0. But then to see why the coefficient of restitution actually works, why is it 1 for conservation of energy? It's a little bit of a derivation. I'm just going to walk through it really quickly. It's not anything that you should be required to do, but we start off by equating the kinetic energies before and after, and then group the A's together and then the B's together. And then we do a little factoring because we recognize that after we factor out a common factor of m, then we're going to have a difference of 2 squares, right? So that's where this comes from. The difference multiplied by the sum gives us this VA squared plus V prime squared. Now, pausing right here, we can come back and take a look at conservation momentum, which we know is always true. And this is total momentum before equals total momentum after. We can do the same trick. We can group the A's together and the B's together. And when we take a look at this term, I see it showing up here. And then this term shows up here. So I can actually divide this equation by this one. That's legal, because if the numerators are equal and the denominators are equal, then the two fractions are equal. So that means that this and this term, they cancel out. These two also cancel out. And I'm just left with the sum of the velocity before and after for A is equal to the sum of the velocities before and after for B. And that's only in the case of an elastic collision. So we rearrange a little bit. This time we're going to group afters and befores, and then that's equal to 1. So the difference between the velocities after divided by the difference between the velocities before is what we call the coefficient of restitution. And so for an elastic collision, that gives us one extra piece of information. Here's an example. We have a 2 kilogram object coming in at 3 and 4 kilogram object coming in at 1. Find the velocities after the fact, so we don't know those. Well, we apply conservation momentum, so 2 times 3, and then 4 times -1, negative indicating it's going to the left, not to the right. And then the velocities after, which we don't know yet. So this is 6 and this is -4, so we can do that really quick. So that's 2, and then divide both sides by 2 to make that extra factor go away. And we see that we have now 1 is equal to VA prime plus 2 VB prime. But we're stuck here because we have 2 unknowns. If we apply the condition for the elastic collision where the coefficient of restitution is 1, and then we put in our numbers, well, in the denominator, we know what's going on. So this is going to be 3 minus -1, which is 4. And now if we express VB prime in terms of VA prime, we can substitute. So this gets substituted into here, and now we can continue our work. So using the distributive property, we get 8 times 2 VA prime, collect like terms, that's 3 VA prime, and that's going to be -7. So VA prime is -70.3. It actually kind of bounces off. And then VB prime goes this way. Which makes sense because the smaller mass is actually going to recoil backward. All right, I hope this example was helpful.